In this video, we will discuss about reinforcement learning in machine learning. We will cover introduction of reinforcement learning, learning models, motivation, reinforcement learning framework, Q, learning algorithm applications, summary. Machine learning is a subset of artificial intelligence where computers learn from data to make predictions or decisions. There are three main types of machine learning: supervised learning, where models learn from labeled data to predict outcomes; unsupervised learning, which finds hidden patterns in unlabeled data; and reinforcement learning, where agents learn by interacting with their environment to maximize rewards. Each type has unique applications, from classifying images and recognizing speech, to clustering data and optimizing strategies in complex environments. Supervised learning is a type of machine learning where models are trained using labeled data. In this approach, the algorithm learns to map input data to the correct output based on examples provided during training. This method is widely used for tasks like classification, where the goal is to assign labels to new inputs, and regression, which involves predicting continuous values. Supervised learning powers many applications, such as image recognition, speech recognition, and spam detection, by enabling systems to learn from past data and make accurate predictions on new, unseen data. Unsupervised learning is a type of machine learning where models are trained using unlabeled data. Without predefined outputs, the algorithm explores the data to find hidden patterns and structures. This approach is commonly used for clustering, which groups similar data points together, and association, which identifies relationships between variables. Unsupervised learning is useful in applications like customer segmentation, anomaly detection, and recommendation systems, enabling insights and data-driven decisions without needing labeled datasets. Reinforcement learning, RL, is a branch of machine learning where an agent learns to make decisions by performing actions in an environment to maximize cumulative rewards. Unlike supervised learning, where the model learns from a fixed dataset, RL relies on trial and error to discover optimal actions through interactions with the environment. It is inspired by behavioral psychology, mimicking how humans and animals learn from consequences of their actions. RL is widely used in various applications, including robotics, game playing, and autonomous vehicles, where it enables systems to adapt and improve performance over time. In reinforcement learning, an agent interacts with an environment to learn optimal behaviors through a process of trial and error. The agent perceives the current state of the environment and takes an action based on a policy, a set of rules, or a strategy. Each action leads to a new state and provides a reward, a signal indicating the success of the action. The goal of the agent is to maximize the cumulative reward over time by refining its policy. This iterative process enables the agent to learn and adapt, making reinforcement learning powerful for tasks like game playing, robotics, and autonomous driving. Supervised and unsupervised learning fail in many situations. Examples are as follows: flight control systems for a set of all sensor readings at a given time, deciding how the flight controls should function. In case of supervised learning, the labels for many features are unknown. Performing trial and error interactions with the environment. Reinforcement learning is capable of solving such problems. Learning to ride a bicycle with reinforcement learning. Imagine learning to ride a bicycle using reinforcement learning. In this scenario, the cyclist acts as the agent, and the bicycle and surroundings represent the environment. The agent takes specific actions, such as turning the handlebars right or left. These actions lead to changes in the state of the environment, such as the balance and direction of the bicycle. Actions: turn handlebars right. Turn handlebars left. The agent receives rewards based on the outcomes of these actions. Positive reward: the bicycle is perfectly balanced. Negative reward: the angle between the bicycle and the ground decreases, indicating a loss of balance. The agent's goal is to maximize positive rewards by learning the best policy, or strategy, for balancing the bicycle. Through trial and error, the agent refines its actions to achieve the optimal balance, just like a human learns to ride a bike over time. Inspiration from natural learning. Dopamine, neurohormone occurring in a wide variety of animals, including both vertebrates and invertebrates, regulates and controls behavior by inducing pleasurable effects equivalent to rewards, motivates us to proactively to perform certain activities. Markov decision processes, MDPs, in reinforcement learning. Markov decision processes, MDPs, provide a mathematical framework for modeling decision-making in reinforcement learning environments. MDPs help define the interactions between an agent and its environment over discrete time steps. Key components of MDPs, states, as a discrete set of all possible states of the environment. Actions, a discrete set of all possible actions an agent can take. Process, at each discrete time step. T, the agent observes the current state. Is an element of. St. Is an element of S and selects an action. Is an element of. At, is an element of A. The agent receives a reward. Rt. Based on the current state and action. The state of the environment transitions to a new state. Plus 1, St plus 1. Markov assumptions, the next state. Plus 1, St plus 1. Is determined by the current state. St. And the action. At. Typically represented as. Plus 1 equals. Delta. St plus 1. Equals delta, St. At. The reward. Rt. Depends on the current state. St. And the action. At. Typically represented as. Equals. Rt. Equals R, St. At. Challenges, the transition function delta. Delta and the reward function. R are usually unknown to the learner. The functions delta and R can also be non-deterministic, meaning the same action in the same state can result in different outcomes and rewards due to randomness. MDPs are essential for developing algorithms that help agents learn optimal policies, enabling them to make the best decisions to maximize cumulative rewards over time. Model-free methods. Model-free methods learn a policy directly from the environment without needing an internal model of the environment. These methods focus on mapping states to actions based on experience. Characteristics, no need for the environment's model. Learn through trial and error. Example, Q-learning, an algorithm that learns the value of action state pairs based on received rewards. Model-based methods. Model-based methods create an internal model of the environment, which includes the transition probability function and the reward function. The agent estimates this model interactively and uses it to calculate the optimal policy. Characteristics require estimating the environment's model. Use the model to predict future states and rewards. Calculate policies based on the estimated model. Example, DynaQ combines model-free Q-learning with model-based planning. Comparison, knowledge of the environment, model-free, no need to estimate transition and reward functions. Model-based, requires estimating transition and reward functions. Learning approach, model-free, direct policy learning through interaction. Model-based, indirect policy learning via model estimation. Examples, model-free, Q-learning, SURSA. Model-based, DynaQ, applications. Model-free methods are simpler and suitable when estimating the environment's model is complex or infeasible. They require more interactions with the environment. Model-based methods are more data efficient, requiring additional computational effort but enabling more informed decision-making. Precise goal maximization of long-term reward. An optimal policy has to be learned in order to do this. Long-term reward may have different interpretations according to how the future is taken into account, i.e. different models of optimal behavior. Models of optimal behavior, 3 main models. Finite horizon model, optimize the reward for the next h steps. RT represents the reward for the t plus 1. The action performed h equals 1 represents a greedy strategy. Models of optimal behavior, 2. Infinite horizon discounted model models future rewards being less valuable than in the present, has infinite horizon, i.e. considers infinite actions in the future, makes use of a discount factor g between 0 and 1, which represents the importance of the future. This is the model used in the Q-learning algorithm. Please check part 2 for next details. Don't forget to subscribe.